Welcome to the TI Precision Lab series on light sensing. My name is Roland Gordon, and I am an applications engineer for Texas Instruments optical sensors. This video will discuss the use of light sensors in applications that adjust the brightness of a display. For the best user experience, for years, many applications have used light sensors to help perform display brightness adjustment. Users like the display to be lit comfortably so it is easy to see and not a strain on the eyes. Based on the surrounding light in the environment, a light sensor is used to set the display brightness. In addition, especially in portable display applications, a light sensor also helps optimize the power consumption to conserve battery life. As the market trends towards adding more displays to everyday applications, display brightness adjustment has become prevalent in many applications. In the personal electronics space, large displays such as TVs, laptops, and tablets really benefit from what a light sensor can bring because people often spend a lot of time looking at these type of displays in many different lighting conditions. Even more so, smaller, ultra-portable displays such as smartwatches, handheld gaming consoles, and smartphones benefit from a light sensor because battery life and outdoor display performance is very important. In industrial applications such as smart thermostats, refrigerators, CPAP machines, point-of-sale machines, remote controls, and many more, displays have been adopted into their systems. This makes the application more user-friendly, and a light sensor enables great user experience when looking at the displays. As everyday applications continue to implement displays into their systems, the need for light sensors continues to grow. In display brightness control applications, the light sensor measures the ambient light intensity, or lux value. Based on the sensor reading, the appropriate display brightness setting is determined, typically by a microprocessor in the system, and the display is adjusted accordingly. The mapping between the display brightness and the sensor ambient lux level reading will vary from display to display. Therefore, the mapping needs to be determined from testing on the display used. For example, a linear or cubed root equation, as shown in the plot, or a lookup table can be used to determine the optimal brightness setting based on the ambient conditions. An additional consideration is how often to update the display. The sensor characteristics such as resolution and data rate will affect how often and quickly the display is able to be updated in response to a change in light level. As covered in the next chapter of this series, the light sensor resolution determines the minimum lux level that can be detected by the sensor. This also determines the minimum change in ambient light that the display can respond to. If the light sensor is placed behind a dark material for aesthetics, the light reaching the sensor is attenuated, which requires a higher resolution sensor to achieve the same performance. For this reason, the light sensor resolution is an important spec for this application. For example, giving a sensor with 100 millilux of resolution behind a 1% transmissive dark glass, the resolution will become 10 lux. Taking the linear mapping from the previous slide, the effect of a 10 lux resolution is shown in the plot to the right. Using TI's OPT 3004, which has a resolution of 10 millilux, the resolution becomes 1 lux. Using TI's OPT 4001, which has a resolution of 312 microlux, the resolution becomes 3 millilux. This increased resolution allows even darker glass to be used while maintaining the same performance. More details on resolution can be found in the next chapter of this series. Because the light sensor is used to adjust the display, there may be restrictions from the minimum data rate from the sensor. If the sensor takes too long to update, the display can remain bright when an environment gets dark, or vice versa, resulting in poor performance and user experience. For this reason, the speed of the light sensor is an important spec to consider. The plots on the right show a fast transition in lux level, as will be seen from walking from outdoors on a sunny day to indoors. Using a sensor with a 3-second conversion time, the display will not start to change until around 3 seconds after the transition. Additionally, display brightness is often smoothly transitioned for user experience, which adds an additional second in this case. This example illustrates the importance of an adequate data rate. Taking TI's OPT3004 as an example, which supports both 800 and 100 millisecond conversion times, this response can be reduced to the display starting to change as quickly as 100 milliseconds after the transition. An additional consideration is the relationship of data rate and conversion time as well as noise, which are all mentioned in the figures of merit video in the next chapter. At faster data rates, the resolution of the sensor may be impacted. For example, for TI's OPT3004, the resolution changes from 10 millilux to 80 millilux at 100 millisecond conversion time. This allows for good performance behind many dark glass materials. However, with the 2% glass, this resolution will be 4 lux, which may not be acceptable. In this case, a different sensor, such as TI's OPT4001, may be needed, which gives 2.5 millilux resolution at 100 milliseconds. Here, using a 2% glass will give 125 millilux of resolution at 100 milliseconds. As mentioned previously and covered in further detail in the next chapter of this series, the spectral response matching of the photopic curve will impact the sensor accuracy. As such, human eye matching is an important spec to ensure the accurate measurements and proper display brightness setting. Here, the OPT4001 spectral response is shown with respect to the human eye response. Good matching to the human eye curve will ensure that the display adapts correctly under all lighting conditions, such as outdoors and under different types of indoor light source types. Finally, in space-constrained applications, the sensor package size can be important. Sensor packages such as TI's DTS and DMP packages are around 200 millimeters in length and width and under 1 millimeter in height. This is small enough for most applications. However, in some extremely space-constrained applications, such as smartwatches, both the PCB area and thickness are important. In this case, wafer chip scale packages such as TI's OPT3007 and OPT4001YMN are more desirable. With a smaller than 1 millimeter square footprint, along with an extremely thin 200 micron height, a wafer chip scale package is an excellent choice. Further details on the wafer chip scale package is discussed in the video on top and bottom facing sensors in the following chapter of this series. To find more light sensor technical resources and to search TI's products, please visit the link shown. Thanks for taking the time to watch this video. Please try the following quiz. Why might a linear mapping between display brightness setting and the ambient lux level not be ideal? Select all that apply. Human eyes do not respond linearly to lux levels, and display brightness settings are not always linear with the display brightness. These are a couple of reasons why a linear mapping between display brightness setting and ambient lux level may not be ideal.